Let's spend some time on our second to last day of Physics 20 now, reviewing our circular motion and gravitation stuff. We've talked about these first few terms quite a lot now, because in our last 2 units, we've seen them, both simple harmonic motion and waves. We just wrote our unit test on that last week, but also within circular motion and gravitation. And if you remember, this is where we introduced these terms, frequency and period. You remember that frequency is the opposite of period. Period is a time. Frequency is, I was going to say a frequency. Yeah, of course it's a frequency. Frequency is how often something happens. Specifically, we're going to say that the frequency is the number of cycles per second. The number of cycles of something per second. Now, in the context of circular motion, we'd say that cycle is a revolution or a rotation, the number of rotations per second. In the context of simple harmonic motion, it might be the amount of times the pendulum goes back and forth per second, or the amount of times the spring vibrates back and forth per second. In general, we're going to say it's the number of times, the number of cycles per second. And we're going to write a little equation that's not on our data sheet, that's really just a mathematical statement of that definition. It's the number of cycles per time. Now, when we went over our simple harmonic motion waves unit test on Friday, we talked a little bit about this. The fact that when you did circular motion and gravitation, lots of you guys messed up on frequency and period, and you got the two mixed up. But by the time you get to simple harmonic motion waves, you did a much better job of that. Okay, let's progress even further. Let's do a perfect job on that. When we see this on our unit test, and make sure that you get the difference between frequency and period. Frequency is number of cycles over the time. Period is the time for one cycle. So it's going to be time over the number of cycles. We get so used to seeing equations on our data sheet, and these ones aren't there. So sometimes we get messed up with those. But we're getting better. Now, of course, because they're the exact opposite, we can relate the two together using the equation T is equal to 1 over F. Period, not time, period is the time for one cycle, and it's 1 over the frequency, which of course, this red circled or red squared off 1 is on your data sheet. By the way, what are the units for period? What are the units that we would typically have for period? Yep. Seconds usually. It could be something else, right? But usually it's going to be seconds. The units that we're almost always going to have for frequency, if time is in seconds, then frequency would be cycles per second, or what's the other set of units? Hertz. Yeah, 1 hertz. You don't say 1 hertz. Kind of sounds weird to say 1 hertz, but it kind of sounds weird to say 1 hertz as well, right? 1 hertz, okay, is 1 cycle per second, 1 revolution per second, 1 back and forth motion per second. Finally, within the context of uniform circular motion and gravitation, we talked about speed of an object undergoing circular motion. And the speed of an object, uniform circular motion, uniform means constant, so it's constant speed. We can describe it by d over t, but we can tailor that equation to look like this. The distance is the circumference, 2 pi r. The time is the period. So it becomes 2 pi r over t. That one's on your data sheet as well. What's that word centripetal mean? Miles, what does centripetal mean? Center-seeking, yeah. So if we have a centripetal acceleration, it means we have a center-seeking acceleration. We'd say our direction of that acceleration is toward the center of the circle. Can anybody explain to me how we can have an acceleration toward the center of a circle when the speed of the object isn't changing? I mean, that's the whole thing about uniform circular motion, is we're going around in a circle at a constant speed. How can we have an acceleration if our speed isn't changing, Rosie? Good. Acceleration is defined as the rate of change of velocity, not the rate of change of speed. Rate of change of velocity means that that includes both the speed and the direction. And because you're going around in a circle, the direction's always changing. There's going to be an acceleration directed toward the center of the circle. The equation for centripetal acceleration, v squared over r. What is it? And that's on your data sheet, by the way. What is that? What do those two little lines on either side of the A represent? Corey, what does it mean when we put those absolute value signs? Whoops. What does it mean when we put those two vertical lines on either side of the A? Yeah. In the end, there is a direction associated with the centripetal acceleration, right? It's toward the center of the circle. But the equation isn't going to give it to me. The equation won't tell me what the direction is. That's okay, because we know which direction it is already. It's toward the center of the circle. But when I put those vertical lines on either side of the A, it means that we're finding the absolute value of the centripetal acceleration. Okay? We're always going to make it positive, regardless of which direction that it is. The units, of course, would be meters per second squared, the same as they are for any other acceleration. Centripetal force, real similar here. It's a center-seeking force directed toward the center of the circle. And that centripetal force, well, any force is m times a, but if we make this m times a, then m times v squared over r becomes mv squared over r. How can you have a force directed toward the center of the circle? Well, let's think about what possibly can cause that centripetal force, which, remember, is never a fundamental force, right? It's always caused by something else. Okay, in the case of my keys going around my head, it's caused by my hand. Where's my hand? In the middle of the circle. Okay, if my hand is pulling on these keys to keep them in a circle, then that centripetal force must be toward my hand, which is in the middle of the circle. Okay, the centripetal force is toward the center of the circle, toward my hand. So let's kind of summarize these last three things here. Let's say we've got an object going around in a circle like this. Okay, it's going counterclockwise around the circle. Okay, I want to identify in red the direction of the centripetal force. I want to identify in green the direction of the centripetal acceleration. And I want to identify in blue the direction of the velocity. So let's draw a green arrow here. Which way is the centripetal acceleration pointing when I'm at the left side of the circle there? Stefan? Toward the center. So let's draw my green arrow toward the center of the circle. Which way would my red arrow be? My centripetal force be? Well, did you get that one? The red arrow, which way is it going to be? Good, toward the center of the circle as well. Same direction as the acceleration, right? Acceleration is always in the same direction as the force, regardless of whether you're talking about centripetal acceleration and force or not. Okay, A and F will always be in the same direction. What about V, the velocity? David? Yeah, we call it a tangent to the circle. That's a line that kind of skips along the outer part of the circle. Okay, at that point, it would be like this. Now, if we were looking for the velocity of an object, the direction of the velocity right here, then we would say it's up like this. The velocity is always a tangent to the circle, whereas the acceleration of the velocity, sorry, the acceleration and the force are always toward the center of the circle. That's the kind of thing you could see in a multiple choice question, right? Okay, again, we talk about, you get 25 multiple choice questions. You guys aren't as good at multiple choice questions. As you're going through things and studying, try to pick out things that would make good multiple choice questions, right? Something like that makes a good multiple choice question. I'm not trying to give you a hint there, because I don't remember if that appears as a multiple choice question, something like that or not. Okay, I know that it has on a unit test. Okay, it makes a good multiple choice question. You know, there's lots of things that do. We're not going to see it all, but certainly some of it we will. Centrifugal force. And I have that force, centrifugal force, in quotation marks. How come? Why did I put that in quotation marks? Because Yeah, it's not really a force, right? Centrifugal force is that outward force pushes outward from the center of the circle, but it's not really a force. It's really just your inertia. Your inertia wants to take you in a straight line, right? Okay, you go in a straight line, which makes you appear to go to the outer edge of the circle. And when you get to the outer part of the circle, okay, maybe something's pushing you in. It feels like you're being pushed out, but you're not really being pushed out. It's what we call a pseudo force. When we talked about this in class, right? When you're sitting at a stop sign and you hit from behind, you get rear-ended at the stop sign, and it feels like you're being pushed back into your seat. You're not. You're accelerating forward, which makes you feel like you're being pushed backwards. Okay, when we're being pushed inward toward the center of the circle, it feels like we're being pushed outward toward the outside of the circle. We're not really. It's really just our inertia that's taking us out there, but it feels like we are. All right. Next big thing, vertical circular motion. When we analyze vertical circular motion, we're going to analyze the object going, we're going to assume that uniform circular motion, even though that's not quite true because it does speed up and slow down as it goes up in height and down in height. Okay. We're going to assume uniform circular motion, constant speed as it goes around the circle. We're going to analyze two spots, the top and the bottom. And we're going to draw a free body diagram every single time we have one of those problems. If we're analyzing the top, the free body diagram is going to look like this. The normal force is going to act down. The force of gravity is going to act down. If we're analyzing the bottom, then we're going to say the normal force is acting up and the force of gravity is acting down. When you're at the bottom of the circle, the normal force always has to be bigger, because if it isn't, it's not going to stay in a circle. The force toward the center has to be bigger than the force that's acting away from there. Otherwise, you're not going to be in a circle, right? I mean, sometimes that could happen, I guess, but if it does, it's not going to be a vertical circular motion problem because you're not going to be moving in a circle anymore. Regardless of whether we're analyzing the top or the bottom of the circle, we need to set F net equal to the sum of the forces. So, in both cases, F net will be equal to Fn plus Fg, just like we did a lot yesterday when we reviewed our dynamics unit. Then we set F net equal to usually m times a, but in this case, m times a ends up being the same thing as mv squared over r. And we'll just sub in mg for the force of gravity. Same deal over here. Let's replace Fg again with m times g. Now we got to worry about signs, positives and negatives. Hey, when you're at the top of the circle, Dylan, when you're at the top of the circle, which way does gravity act when you're at the top of the circle? Down. So let's make that a negative value. Not when we're writing out the equation, but when we sub in the numbers, let's make it a negative value. When you're at the top of the circle, Kristen, when you're at the top of the circle, which way does the normal force act? Downwards. So we're going to make that negative as well. Good. And Everett, when you're at the top of the circle, which way is the net force, the centripetal force? It's downward. So we're going to make them all negative when you're at the top of the circle, right? Look, if you got two downward forces, the net force or the centripetal force must be downward. Let's look at the bottom of the circle here now. Cameron, at the bottom of the circle, which way does the normal force act? Yeah, so we're going to make that positive this time, right? Gravity is still going to be negative, but we're going to make the normal force positive. When you're at the bottom of the circle, here's the hardest question yet on this stuff. When you're at the bottom of the circle, which way is the centripetal force? The mv squared over r. The net force, part of it's up, part of it's down. What's the total, up or down? Yep, good. It's going to be up. We know that because if you're moving in a circle, the net force has to be toward the center of the circle, and the center of the circle is upwards from you. So what are you going to be asked to solve for here? Well, a lot of times you're asked to solve for normal force. just remember that the normal force could also be the force of the track, or something like the force of the track. But it could also be, what's another term that we associate with normal force? We saw this yesterday with elevators, right, Emma? The apparent weight. Any of those things we're going to solve for Fn. Maybe you're asked to solve for the force of the actual weight. The actual weight is just your force of gravity. Listen, it's the actual weight is not your mass. Hey, I have a mass of 70 kilograms. That's not my actual weight. That's my actual mass. If I'm asked for my actual weight, then I'm going to say my actual weight is 70 kilograms times 9.81. So 686 or whatever that works out to be. Your actual weight is just the force of gravity, which is m times g. Listen, if you're asked for your actual weight in one of these questions, it's easier than all of this. You don't need to go through this process of doing circular motion. Actual weight is just mg. Don't try to make it harder than it has to be. Normal force, yeah, you got to go through all this. But force of gravity, you don't. Just say m times g. What else can I be asked to solve for here? Minimum speed. How fast does this roller coaster have to be moving in order to not fall out of the loop? If you're looking for minimum speed, you're going to analyze the top of the circle, and you're going to set Fn, not F net, but Fn, the normal force, equal to 0. Because you guys know from our demonstration that as you're going around in a circle, more than the minimum speed, when you're at the top, gravity and normal force push down. But as you slow down, the normal force doesn't have to push as hard. And as you go the bare minimum speed, just barely able to go around the circle, the normal force doesn't have to push at all. So the force of gravity provides all of the centripetal force at that point. So looking for minimum speed, just solve, analyze the top of the circle right up here, and set Fn equal to 0. But don't always set Fn equal to 0, just when you're looking for minimum speed. There's another 6 points that we have on our test. Now we're at 31. 31 out of 56 for the written portion of the test, or 31 out of 81 for the whole test. Well, when we talk about things that we could be asked in multiple choice, I mean, we're definitely there right now. Right? We talk about heavenly motion. Aristotle, remember Aristotle was the heliocentric guy. What does helio mean? Sun-centered, right? Everything revolves around the sun. The Earth, the moon, all the other planets, all the other stars revolve around sun. That's wrong, actually. Aristotle wasn't the heliocentric guy, was he? Aristotle was the geocentric guy. Good. I'm going to pretend I made that mistake on purpose, but be careful. What does geo mean, David? Earth, right? Everything, the sun, the moon, all the other planets, all the other stars revolve around the Earth, the geocentric model of the universe. And then we fast forward a couple thousand years to Copernicus, who talked about the heliocentric, and we already know what that means because we just talked about it. The sun-centered. The Earth and all the other planets revolve around the sun, which is the way we know it to be now, right? Fast forward a little while later, Tycho Brahe, what's he known for? He's the P guy. He's the guy that goes to his dinner party, decides it would be rude to leave and go to the bathroom, so I'm just going to hold my pee, and he ends up dying of a bladder infection a couple weeks later on. But you know what? That's not the really important thing about him. The really important thing about him is that he made observations. naked eye observations of the heavens, angles and times and so on. Didn't do anything with it. But he made these observations. And those observations led his assistant, Johann Kepler, who we talked about more than any of the other guys, to devise 3 laws describing the motion of the planets. So Johann Kepler devised 3 laws. There was, first of all, the law of elliptical orbits. The Earth revolves in an ellipse around the sun. There's 2 focal points. The sun is at one of those ellipses. Sorry, one of those focal points. The second law said, it was called the law of equal areas. If we draw a line joining the sun to the Earth, it's going to sweep out a certain area in a certain time that we're going to call T1. Fast forward a few months, another time T2 sweeps out another area A2. If the times are the same, if T1 equals T2, then A1 equals A2. So we say that in words, during equal time intervals, a line that joins the sun to the Earth sweeps out equal areas. What's the big deal with that? Well, we talked about the speed of the Earth, right? And how we know that if T1 equals T2 here, then the Earth must be traveling faster when it's closer to the sun than when it's further away from the sun. And finally, the third one, called the law of periods. Says basically, we've got a constant called Kepler's constant. It's equal to t squared over r cubed. Kepler's constant is the same for anything revolving around the sun. T squared over r cubed for the Earth revolving around the sun gives you a certain k. T squared over r cubed for Jupiter revolving around the sun gives you the same value of k as the data about the Earth. So that allows us to find, we didn't do calculations with this, but it would allow us to find data about one planet using data about another planet.